Let me just say this, right? This is a talk online, 2020 virtual workshop on Ricci curvature and scalar curvature. First, I would like to thank the organizer for the invitation, especially this workshop is in honor Professor Misha Gromov 75th birthday. I first met Professor Gromov when I was a graduate student at Stony Brook. That is from 86 to 90. I think I remember Gromov visit Stony Brook several times and mostly visit my thesis advisor, Jeff Chigger. So I remember once he gave a talk, Professor Gromov gave a talk. I noticed that Jeff, before the talk, long before the talk started, Jeff sat in the lecture room much earlier, just Jeff, almost like himself. So I realized this is a very important talk. So that's what I remember. I wish I could remember the content, but I don't think I was a graduate student. I didn't understand anything. All right, so let me, before I start, I'd like to share a memory, a photo. I'd like to share a photo with you. I don't get authorized from all the people in the photo, but you can see this is Professor Gromov. Take a camera recorder. And this is 97 at the Rong Institute. And this is Somani and Yang Dagang, Yudunu, author. I don't remember his last name, and Yu Ding. All right, so that's the only picture I think I had. I have another one important, but by the end I will share with you. Okay, so now let's start the talk. How to get it? Okay, close. Okay, the title. Okay, so the title is Collapsed Spaces with Local Bounded Coming Geometry. Okay, abstract. Let me just read this. In 1978, Gromov proved a highly unexpected theorem on almost flat manifolds. It says, right, an almost flat N manifold is diffeomorphic to a nilpotent manifold up to a bounded normal covering space. This result has been a cornerstone in the theory of collapsed manifold with bounded section curvature, mainly developed by Chigger, Fukaya, Gromov. We'll discuss some recent generalization of this result to maximally collapse, collapsed manifolds with local bounded Ricci coming geometry, and to maximally collapse Alexandral spaces with local bounded coming geometry. We will introduce the notion during the talk, as well as counterparts of the above collapsing theory in these spaces, right, in manifold and in singular spaces of local bounded coming geometry. Okay, so here is the schedule of the talk. Part 1, the grammar of almost flat manifold, and the collapse manifold with bounded sectional curvature. Part 2, I'll state the main result. And also ask some questions, related questions. Part 3, I outline some of the proofs. I may not be able to get all the proofs, but I hope I can explain some idea, main techniques. Part 1, grammar of almost flat manifold and collapse manifold with bounded section curvature. First, let me reveal almost flat manifold, grammar of almost flat manifold. The theorem says, given fixed integer n, there exists a constant, one is small epsilon n, one is Cn, that's constant depending only on dimension. And this constant satisfies the following. If you have compact n manifold, satisfies right, inequality. It's a section curvature. You take any two plane, you take section curvature times the diameter square. And this number, right, is scaling invariant. If you rescale the metric, this number remain the same. If it's sufficient small, since rescaling invariant equivalently, you can always, right, normalize the section curvature bounded by 1 in absolute value, where the diameter is less than epsilon. Maybe, right, they have square, right. Okay. But this constant takes square root, doesn't matter. It's just depending on n. Then this condition is called almost flat, because right, if flat manifold second curvature identical to 0, no matter how small this constant is, always satisfy this condition. So flat manifold satisfy this. There are no flat manifold, we'll see, also satisfy these conditions. And that's just geometric invariant, very small, right? With scaling invariant. Conclusion is the manifold is diffeomorphic to a homogeneous space, precisely called infernal manifold, where n is simply connected nilpotent Lie group. Gamma is a discrete group of this semi-direct product, such that gamma almost, most part of gamma is translation. So that's a theorem. This is a well-known theorem, famous theorem, has long-lasting consequences. So I don't explain more than that. I just say that this theorem generalizes the classical Bieberbach theorem, which says if section curvature identical to 0, right, manifold compact, so it's a flat manifold, it must be homogeneous space, Euclidean space modeled by discrete subgroup, where in the same form, similar form. All right. The proof, grammar published paper in 10 pages and JDG. However, the proof, because it's involved several fields, not well related fields, very difficult. Then there is a workshop in Germany, I think in Oberwolfer, to discuss the proof. After that, Buscher, Kasher wrote a book, 140 pages, filled all right the details. So the proof is very hard to follow for me. Yeah, for me. And but last year I gave a new proof. The new proof means I quite different from the proof Gromov. Then later rule strengthens the theorem by saying it's a diffeomorphic, right? Gromov original just say up to a bounded normal carrying, it's a nilpotent manifold. But it didn't like the stronger sense state here. That's for the rules work. He construct right, flat connection with parallel torsion. Using that PD techniques, he get a stronger version based on Gromov's theorem. Okay, so my proof is quite different, and some idea actually will be presented in this talk. So I like to say this nilpotent manifold actually satisfy the condition. I just want to quickly go through this. It's called inhomogeneous rescaling or scaling. I should say scaling, right? If you let n simply connect nilpotent Lie group and gamma is co-compact lattice, then we know nilpotent Lie group has a normal descending sequence where each ni is the commutator with s commutator with, right? You iterate this. Then you have a Lie algebra, corresponding Lie algebra has a graded Lie algebra, then you have a graded basis, right? E1, ES1, ESKS is a basis, Lie algebra for the last one. Then you go up. Then for any small epsilon, you can define one parameter left invariant metric in this form. If you take a basis, right, extend, this is a basis for the Lie algebra, but graded basis. Depending on which level, you rescale different factor, different rate, like this. Then it's not hard to check. Second curvature is bounded, let's say bounded by 1. It's by constant, right, depending on the commutators, coefficients, but it's bounded. Then if you let epsilon go to 0, right, the every direction rescale, right, shrink to 0, but each direction shrink different rate. It's called inhomogeneous rescaling, right? So along different levels, you scale different rate, exponentially different rate. So to maintain the curvature bounded. To maintain the curvature bound. All right, so that's a very concrete example. Gromov theorem says, right, if you have, right, the diameter go to 0, curvature bound, then it's up to a finite normal carrying, it's nilpotent. All right, so since Gromov theorem, the study on class manifold with bounded section curvature has taken off, and so mainly done by Chigger, Gromov, and Fukaya, and later the two different approach combined. So now here, since only related to what in this talk I restrict to bounded diameter as well. So now we extend Gromov almost flat manifold theorem to a parameterized version. So you're assuming a sequence compact manifold collapses in Gromov Hausdorff distance topology to a lower dimensional metric space, where the sequence has uniform bound section curvature and uniform bound diameter. So the X has a diameter less than or equal to D. Now, the conclusion, right? If X is a point, Gromov already have a theorem. But if X is not a point, right, but diameter less equal to D, then the following statement is true. Then you can have O1, right, the dimension is N, invariant nilpotent fibration map. And fibration map also epsilon I Gromov-Hausdorff approximation at almost preserved distance. So if I combine manifold collapses to a lower dimension metric space, then on the frame bundle, once you fix bi-invariant metric on the fiber on, right, the orthogonal frame, then there is a canonical metric on the frame bundle. And this frame bundle, right, passing to a subsequence, also Gromov-Hausdorff convert to something. And Gromov-Hausdorff convergence about distance convergence. So the symmetry, the distance symmetry, right, also convert to a symmetry on the limit metric. So you have this equivalent convergence. The theorem says on the frame bundle level, you can have a smooth fiber bundle map where the fiber is nilpotent manifold. The fiber is nilpotent manifold. It's no longer infinite. And the regularity, the bundle map is the second fundamental uniform bound. And this map is not Riemann submersion, but we call epsilon almost Riemann submersion, where Ci denote the horizontal vector to the fiber. Okay, so they have, say, if you collapse with bundle diameter, then on the frame bundle, you have nilpotent fibration, where fiber is nilpotent manifold. This can be viewed as parametric version, bundle version of Gromov almost flat manifold theorem. So why now like to add one comment? Why people study collapse manifold, right? When I say this is collapse means the volume convert to 0. So why? Because one reason is if you fix dimension, the diameter and the volume, then you consider all the n-dimensional manifold satisfies these bounds. Then trigger finite theorem says there are only at the most finite number depending on these parameters, many diffeomorphic types, right? So only finite many not collapse if you fix diameter. Infinite many, we know that fix each dimension, there are infinite many manifolds satisfy this if n is at least bigger or equal to 3, right? Then these indicate that study collapse manifold is very important. Okay. Now I'd like to say quickly a few applications, right? The application of this fibration theorem. One is the result myself, fixed dimension, fixed pinching. Then you can have two constants. One depending on the pinching, one is not. If given any n-dimensional delta pinch manifold, means section curvature between delta and 1, then you can say things about fundamental structure, fundamental group. Either the fundamental group is not large, means it's upper bound. The number is upper bound by this constant, right? It's a finite, right? It's this fundamental finite. Either the number is bounded, or the fundamental group is almost cyclic, means has cyclic subgroup index less or equal to Cn. So virtually cyclic. So from the statement, right, there's nothing really related to collapsing, but in the proof, it's use the vibration theorem. Another one is this. It's due to Fu Quanfeng, myself, and Petrunin Tushma. Right. It says compact N-manifold satisfying curvature bound, diameter bound, but no volume bound. If no volume bound, it could be infinitely many, right? As I said. But if you put topological constraint, fundamental group, second homotopy group are trivial, right? And then this class only have finite many diffeomorphic types. All right. So obvious fundamental group condition is necessary to have finite many, but there are examples if pi 2 is now trivial, there are infinitely many satisfy this condition. So the pi 2 is, again, from the statement theorem, there's nothing involved collapsing and vibration theorem, but in the proof, it play important role. Okay. Now, after review the collapse manifold which bound the section curvature, the next thing you want to do is extend the study collapsing with weaker curvature conditions, right? Now let's see. But the first thing you have to do is you need to study under weak curvature condition. You want to understand maximally collapsed manifold, means diameter very small with weak curvature condition. So there are a few options: section curvature bound below, Ricci curvature bound in absolute value, and Ricci bound below. Maximally collapsed means under this normalized curvature condition, diameter is small. Now, how to study this class manifold, maximally collapsed? It's include, if section curvature bigger equal -1, it's include, right, all compact manifold with non-negative section curvature. Because non-negative with skewed diameter, with skewed metric, the curvature condition preserved, but diameter can be arbitrarily small. Ricci flat manifold corresponding to this, and Ricci non-negative, right? Each of the class has contain a lot of manifold. It's far from classification, right? So you cannot expect some result like as clean as almost flat manifold. But under these conditions, right, what can be said? There are some weak version, right? On the fundamental level, nilpotent. It's called generalized Margulis lemma. I'll state this, right? If the manifold maximally collapse, means under the Ricci curvature condition, bound below maximum collapse, almost to a point, then the theorem says then the fundamental group is Cn nilpotent, means highest nilpotent subgroup index the most Cn, right? This can be viewed as a fundamental group version of almost flat manifold. Early work I'd like to mention is Fukaya, Yamaguchi, and Kapovich, Petrunin, and Tushma. Right? They deal with section curvature bound below. Okay. Now, what else? We know that maximally collapse, but what about vibration, right? Then Yamaguchi proved this, right? If you have a manifold compact, right, collapse to a lower dimensional Riemannian manifold, which is compact, that means you have bounded diameter. Then the conclusion is there is a vibration map. C1 bundle map, and there is some kind regularity. It's called almost Lipschitz submersion. Right? It's not as strong as second fundamental form bond, but right. So because the missing part maximally collapsed manifold, right? The fiber is almost maximally collapsed. So even though its induced metric on fiber may not have section curvature bound below, there are no other than fundamental group. There are no topological constraint on the fiber in general. Now, what about Ricci curvature? Right? If you have a sequence Ricci curvature bound below or bound the absolute value, right, collapse to a lower dimension Riemannian manifold, do you have the fibration? Anderson say no. He constructed example on manifold, almost Ricci flat, right? It's a collapse to a flat torus, compact torus. But this manifold is not K-1, so you cannot have S1 fibration because the dimension here is -1. So Ricci curvature, even both side bound, cannot expect bundle fibration. Okay. Now, now we just review some brief review these situations. Now, we like to propose a study, or we already study the class called spaces with local bounded coming geometry. I like to review the concept. X here denotes a complete length metric space. The example of in this talk is Riemannian manifold. O is Alexander space. And what is so-called local bounded common geometry? That means you take a point on the manifold, then you look above, right? Then you look the universal cover of the bow, because bow is path connected. So you have universal cover. Then at the reference point, this bow is contained in universal cover. So we call this bow the rewinding bow of the bow, original bow. You have a bow upstairs, right? And we call the volume of the rewinding bow the local rewinding volume. So if you have a bow, right, you have two volumes. One is its original volume, right? In this case, we could say Hausdorff measure. Right? We assume the Hausdorff measure exists. And also, you could have another so-called rewinding volume. These two volumes, rewinding volume always bigger, equal to the volume. And equal if the bow itself is simply connected. So universal cover is just itself. And we say that X, I shouldn't say M, this is a misprint. X satisfies local rho-v bounded covering geometry if every point the rewinding volume radius rho is bigger or equal to V. And where this condition come from? So if in the collapsing theory of Chigger, Foucault, Gromov, they have a important property. Given dimension, you can find two numbers, any complete manifold, collapse or not, just complete normalized. Section curvature is bound normalized by 1. Then it satisfies the local rho-v, rho-n, v-n bound covering geometry. Means, right, local bow universal cover, right, is not collapse. And yeah, 2 years ago, I gave this proof relies on Gromov's almost flat manifold theory. I gave a proof independent almost flat manifold theory. It's relatively simple and elementary. Okay. Now I want to emphasize that the class, if it's manifold, right, with Ricci curvature bounded below, this class, it's collapsed with Ricci curvature bounded below, and local rho V bound covering geometry, we call this Ricci covering geometry. It does not imply M admits sitting close metric, nearby metric with bounded section curvature. So on such manifold, right, you cannot expect by smoothing method, you can find nearby metric with bounded section curvature, right? This is an easy example. You take a manifold non-collapse to the n dimension, Ricci bounded below. But we know that if the volume no collapse, the limit could be singular space, right? There are a lot of examples. Now you take the product manifold, it's collapsed to where you shrink the S1 factor, collapse to this, right? So this example satisfy if the original metric has Ricci bounded below, it satisfy, right, rho V bound Ricci covering geometry. But you cannot say that you have a nearby metric bounded section curvature. If that's the case, you get fibration. If you get fibration has to be S1 free action, then the limit space has to be manifold. But here, if you start with this sequence, limit is not manifold, you get contradiction. This example show that this class, rho V bound Ricci covering geometry is different from the section curvature bound, the assumption, because you can't have nearby. All right. Now, to study this rho V bound Ricci covering geometry, I want to say that the trigger coding neighbor theory on Ricci limit space is basic too. Okay, the second part, main result. Okay, so we let me say this, right? We did last year. This is Rong, Kong Ling, and Xu Sheng. Okay, so given dimension n and V positive, we can find a constant. Such that if you have a compact n manifold, it's maximally collapsed. Curvature lower bound below and diameter very small, but we require that rewinding volume, just 1 point rewinding volume is lower bound below by V, and the diameter is small relative to V. Right? It's maximum collapse, but with local bounded Ricci covering geometry. Conclusion is M is diffeomorphic to infranull manifold. With the same constant bound, right? I didn't state another constant, right? But just this diffeomorphic. So if you combine the previous one, right? If section curvature both side bound imply this condition is satisfied, automatically satisfied, the volume condition automatically satisfied, right? For right, then this theorem generalized Gromov almost flat manifold theory. Actually, there however, we couldn't say that because the proof this relied on Gromov theorem. We use the theorem. So the proof is by smoothing method. The key is observe that the remaining universal cover satisfies, right, any unit ball on universal cover is dot Gromov-Hausdorff close to a Euclidean ball semi-radius. So in terminology, this is a Raffenberg condition. So volume condition actually implies in these special circumstances Raffenberg condition. And then we can apply Raffenberg condition. We can apply Perlman pseudolocality to show that the Ricci flows on the universal cover exists for definite time and produce, right, thereby almost flat metric in the sense of Gromov. So if you have you get almost flat metric, then you just apply Gromov theorem. So that's the idea, the proof. And there are previously there are many works on generalized Gromov theorem that's deal with manifold which Ricci, which a certain bound on Ricci, or right on some conditions plus various conditions. So the idea is to show existence a nearby almost flat metric, then apply Gromov theorem. Right. But assume that this condition, we put this local Riemannian volume condition is the most weak condition. All other this work, the condition implies our condition. Okay. After this, the next we'll consider primary transversion, right? Maximum class. Then Fabricius theorem. We have to set up the limit is a compact Riemannian manifold. Satisfying the sequence, satisfying Rho bound Ricci covering geometry. Then Hongzhi Huang, right? He proved that in this case there is a smooth fiber bundle map, and which is a Gromov-Hausdorff approximation. It's almost preserved distance. That means the fiber collapse to a point. So how the proof of this, the construction, the smooth fiber bundle map uses the Chigger coding neighbor theory, right? Precisely the delta, if the dimension n is m, the m delta splitting map, and then use standard partition unit to glue this map. So the key is to verify this map, the tangent map is not degenerate. So how you get this being checked? Here, the condition Rho bounded Ricci common entered to guarantee that, right? If you look at local Riemannian universal cover above, then because the condition is not collapsed, in these circumstances, actually the universal, local universal satisfy the Raffenberger condition. Then, right, by Chigger, Jiang, Menshui Jiang, a neighbor, right, a recent work on canonical Raffenberg method show that, right, if a node collapse, then the n dot splitting map is not degenerate. Now using this, you can get some work, then show that this map is not degenerate. Right? So here, just roughly like this. Now, what about fiber, right? The fiber, what is a fiber, right? The fiber is expected to be infernal manifold. However, because of weak regularity, there's almost no regularity can be said about the F, other than it's not degenerate. So the induced metric on fiber definitely right has no Ricci bound below condition. So fails to conclude that fiber is nilpotent. I want to say that the maximum class, the theorem 1 cannot be applied here because of this situation. Now, then I give a proof about the fiber actually diffeomorphic to infernal manifold. also the struct group can be reduced to alpha, right? This is a strong structure group. So how I did this, right? Actually, I gave a new proof for the theorem 1, so maximum collapse, right? Local Ricci bounded column geometry. In the proof, no smoothing technique is involved, and it's just direct proof. So because of this proof, right, I didn't need apply Gromov almost flat manifold, right? And also, given the fact that I gave a proof for bounded column geometry without involve Gromov theorem, so the new proof will imply almost flat manifold theorem. Now we can say, using the new proof, you generalize Gromov almost flat theory. Oh. Also, I like to just point out some related work. So in color, in theorem 2, right, you can replace this local bounded Ricci common geometry condition by so-called local maximal cyclicity length for the local fundamental group. The fiber is nilpotent, and in this case, right, the fiber is nilpotent. It means the nilpotent has maximal cyclicity. Maximum means the length is equal to the dimension, the difference between dimension m and dimension n. And there are recent beautiful work by Shaoxai Huang and Bing Wang. One result is they get so-called rigidity of first Betti number, right? And if we replace this condition by I mentioned this condition, then our theorem 2 implies their result, right? Actually stronger. Okay. So I like to put a conjecture on this. What about singular fibration? Remember, in bounded section curvature, we have singular fibration. So we conjecture that if we don't assume limited smooth lower dimension manifold, then right, we conjecture there's a continual onto map from the manifold to the space, such as each fiber actually, since the fibration theorem can be applied locally, so for regular point, the fiber is infranull, so that's can be seen. Now each singular fiber, right, means the fiber over a singular point. We conjecture that it's a finite quotient of infranull manifold. It's like an infranull orbifold. This is different from the collapsing theory with bounded section curvature. For singularity, it's basically said the singularity is slightly more singular. I want to mention the related things, right? The recent construction collapsing Calabi-Yau metric on Kähler manifold, right? I mentioned work. And recently, there are many works on constructing collapsing Calabi-Yau matrix. So the construction, many of the construction relied on a nilpotent fibration structure on the manifold. They're using this structure to construct the collapsing, whose regular part is the nilpotent fibration, whose singular part is very singular, means it's not orbifold. Right? So here is so it's different. That means actually you can examine their constructions. The collapsing on regular part actually really satisfies the local bounded Ricci common geometry, because actually in the Ricci flat case, right? The regular part curvature remain bounded. Okay, now Alexander space. I think I'm a little bit slow. Let me just quickly. Alexander space, it's a locally compact dense matrix space, satisfied. It's a singular space, but each point you can find a small neighborhood. In the small neighborhood, you can draw a triangle, right? 3 points, you measure each pair of distance. You see that's a triangle. The triangle, you can, this kappa and this kappa same, you can find on the space form, a space form, 2-dimensional space form, right? Simply connected constant section curvature kappa. You draw a triangle, and that triangle is look, the original triangle is look fatter than comparison triangle. This subject was introduced in the seminar paper by Brago, Gromov, Karman. And there is an ongoing book on this subject. The goal of the Alexander space, like in Riemannian geometry, investigate, interpolate between, well, on the Alexander space between geometric structure and topological structure, right? And similar to the comparison geometry. I want to say that many results in curved comparison Riemannian geometry have found counterpart in Alexander geometry, right? Related to this work is, right, this talk is the stability, permanent stability theorem, right? And also the Margulis lemma last year proved by Shicheng Xu and Xu Chaoyao, right? And Soul theorem, etc. Right? I want to say this workshop is about Ricci curvature and scalar curvature. Now, Alexander space actually has a relation with Ricci curvature, singular space. It's proved by Petrunin and Huichun Zhang and Xiping Zhu later. Given Alexander space, right, compact, it is a major space with curvature, Ricci curvature bound below. In the sense of Lat, Villani, Stoll. So I just mentioned this, right? When we study Alexander space, it's also Ricci curvature bound below, singular space. So the theorem in Alexander space is parallel to this, but keep in mind our main subject is singular space. So given dimension n and this, right, you can find the constant. If you have maximally collapsed in this sense, diameter small, curvature, right? Alexander space curvature bound below in the triangle comparison sense, and rewinding volume is not collapsed. Alexander space has a Hausdorff measure. It's positive. Then it's homeomorphic to an infernal manifold. Homeomorphic. So in the assumption, you start with Alexander space. A priori, it could be singular, but from the conclusion, it's not singular, it's topological manifold. Right. So I have some question like ask. So since Alexander space is singular space, right? Start with, it's a major space with Ricci curvature bound below. Then can you have analog theorem form in the major space, Ricci curvature bound below? So that's the first natural question. The second is, right, it's known that any Alexander space contains a dense subset on which you have a C0 Riemannian structure. And the Riemannian structure induced matrix is isometric to Riemannian distance coincide with induced distance on the subset, which is dense. So the second question is, this set, right, has a Riemannian structure, a C0. Does this Riemannian structure determine a differential structure naturally on the space. Here, I mean the space in theorem 4. If so, is a conclusion, can the conclusion be diffeomorphic? So that's 2 questions. And fibration theorem. Oh, wow, I don't think. A little bit slow. Maybe I'll take a few minutes more. Nilpotent fibration, right? So next you consider a sequence Alexander space curvature bound below same dimension, collapse to a lower dimension space, and this is also Alexander space with the same curvature bound, right? But with the Rho-V bounded local Rho-V bounded common geometry. Small ball, the remaining ball has a lower bound. Now you assume that the limit space, right? Even though the sequence could be very singular, but limit space you have mild singularity means you have some kind of a so-called M dot Stringer length L bigger than 0. So roughly speaking, it says, right, you can have a frame, local frame on the limit space, which the distance function from the frame gave you by Lipschitz homeomorphic to Euclidean space Rn locally. So it has mild geometric singularity. Then for a large, you have 2 conclusions. First, you have bundle map. And the bundle map is Gromov-Hauser approximation. And also it's in the sense of Yamaguchi, it's a Lipschitz submersion, almost Lipschitz submersion. Second, the fiber is homeomorphic to an infernal manifold. Similarly, well, you start with, you assume this may be singular, but conclusion is xi, I'm sorry, this is I. Xi is a topological manifold because the base space is a topological manifold, the fiber is topological manifold, so total space topological manifold. Okay. I like to say that the fiber bundle map is based on Yamaguchi's work and most recent work, Fujioka. So it's basically their work. So I just adapt to this volume, local rewinding volume conditions. To conclude, the fiber is infernal does not follow from previous theorem, right? Maximum collapse. Again, by the same reason, right? No regularity on the fiber. So the induced matrix on fiber may not be Alexander sense, curvature bound below. So that's you have to work, right? You have to basically get a proof, run the proof of theorem 3 in this setup. Okay. Similarly, we have singular. We have a conjecture on singularity. So if you do not assume this has mild singularity, just general Alexander space, with same condition, you have continuum map. Each fiber here, we conjecturize homeomorphic to an infernal manifold. Okay. So I like to give an example where you can see right, how you get the limit space singular, total space singular, but fiber is not singular, right? This is the conjecture says fiber homeomorphic. So that's easy to construct. You get you assume have compact manifold, assume it means torus action without fixed point. Then you know that this manifold means one parameter family immanent matrix, such as collapse to orbit space with boundary section curvature. Right, this is known. And not only that, you have boundary curvature, the local rewinding, local boundary common geometry automatically satisfied. Now, assuming action, assuming you have a finite entropy group, it's not trivial. Then you take a the manifold, take a quotient, right? This is invariant matrix, you can take a quotient space, we have an induced matrix. Then that is Alexander space, right? Since you have a isotropic group, so the quotient space may not be singular, should be singular, right, in general. Then still collapse to the limit space. It's singular, and total space is singular, limit space singular, but the fiber, what's the fiber? The fiber just torus modular finite group. It's still a torus, right? Still a torus. Right. So it's a manifold. Okay, so that's an example. I have some theorem says singular fibration, one step, but I like to escape. Still checking details, I like to escape, but just basically says there are evidence supporting this due to the time constraint. I have like 5 minutes, maybe I extend to 10 minutes. Let me try to finish the proof. Okay, so this part I like to escape. Outline proof. The tools, I only explain the proof for a Riemannian case where you have a Riemannian manifold, Ricci local bounded Ricci coupling geometry. So what is the tools? First, we'll have a homeomorphic, diffeomorphic characterization of infranuclear manifold, a new manifold. This result is after Gromov homoflat manifold, and some are quite recent. So there are some topological new result. Yeah, I like to use to get the proof. And also, I said the geometric part, right, analytic part, the trigger coding neighbor theorem, Ricci limit space. And the Margulis lemma by Kaipovich Wilking. And there are techniques improving this lemma, so-called zoom-in map technique. And the fibration theorem I mentioned, right, Hongzhi Huang, right, fibration theorem. And equivalent convergence theorem. And also Trigger-Gromov's patching theorem. Let's say this, constructing F structure. All right. So homeomorphic, diffeomorphic criteria for infranuclear manifold. So Ferrier-Xiang, they show that a compact manifold is homeomorphic to infranuclear if the two conditions satisfy. Universal is contractible. Fundamental group contains, universal contractible means the fundamental group is torsion free. Then fundamental contains nilpotent subgroup finite index. So once you know the two conditions, you know it's homeomorphic to an infranuclear. And what about diffeomorphic? It's quite late. It's Nakayama. And a simple proof by Bill Gradick, 18. So compact manifold, diffeomorphic to new manifold means the new manifold, not infranuclear. If only if the manifold admits iterated principal circle bundle. Precisely, the manifold is circle bundle, principal circle bundle. The base space is a principal circle bundle until iterate n times until the base space become a point. The last one, trivial circle bundle over point. And this diffeomorphic criteria is not well fit our purpose. So I gave a alternative criteria. So a manifold is diffeomorphic to new manifold if and only if the following is true. M admits a sequence of subbundles with fiber, right? Subbundle. The first fiber bundle is F1. The second sub bundle, the fiber is sitting in the first fiber, and etc. So you have a first bundle, right? You have second bundle, you have a last bundle. The base space, the dimension of the second one is bigger than first one because the fiber is smaller the first one. Then the base space, the second one, is a principal bundle over the first one. You have a additional structure. Okay, so so that's the criteria. So in the proof, I basically try to establish the structure, this structure and all the Faro Shanks criteria. Okay, so what's the idea? So let's see. I have a few pages. Let me extend. So maybe a few minutes more, maybe 10. Let me just quickly get the idea. So the idea is you want to prove theorem. Let's just try to prove theorem 1. Theorem 1 says maximally collapsed to a point if you have a universal is not collapsed, right? Ricci bound below. So we will prove using the compactness. We can try to prove this situation. You have sequence collapse to a point, right? So use the compactness argument. If you can show that for I large, then this sequence satisfies this condition. So you want to show that I large, this is right diffeomorphic to infinite manifold. That's all you need to show. So first lemma, we observe that right the diameter go to 0 if you rescale the diameter to rescale the inverse of diameter, right? Blow up this to a point, blow up diameter to 1, then passing to a subsequence, you can get this regularity, right? This limit space has diameter 1, but on the universal cover, the equivalent conversion to the Euclidean space, because you blow up the limit, the Ricci curvature actually lower bound go to 0, right? So we call this uniform dot I Ramberg, where dot I go to 0 as I large, and uniform Ramberg, you mean any unit ball you have satisfied. It's very close to Euclidean unit ball, right, with the so-called Ramberg. Any rescaling, that's the closeness remain the same. So it's called Ramberg condition. And with this setup, easy to show that a finite abundant normal covering, basically based on Bierbach theorem, this sequence, right? Oh, I should put the rescaling constant. It's convert to flat torus, flat torus. So you have smooth limit basically using this. Then you can apply the fiber bundle theorem. You get a fiber bundle, fiber. Then you look just fixed point, you look the fiber, you try to rescale the fiber intrinsic diameter to 1. Then you blow up again, right? Then you do this iteratively analyze this, you can get the second property that's important. So for a large, right, the sequence each fixed I admits so-called semi-iterated bound over tori. So the total space, just like the first step it says, right? Total space is bundle over tori. If you blow up the fiber, the finite normal cover fiber convert to a flat. I mean, not convert to flat, but you can see it has a bundle or flat tori iterated like this. Now, so each blow up, you really have to analyze the sequence, the whole sequence, instead of not the second fundamental for not the fiber, because there are no induced matter on fiber has no curvature lower bounds, Ricci curvature. But anyway, you can prove this. A consequence of the easy to show that each of the fiber is diffeomorphic to Euclidean space, universal is diffeomorphic. Once you establish this, you get homeomorphic to infinite manifold. Corollary, this is homeomorphic to infinite. Why? Because Magulus lemma plus lemma 2, the universal is right is Euclidean. So it satisfies Farichon's criteria. So it's homeomorphic to infinite manifold. Okay. Now the most difficult part is to show that it's diffeomorphic. The finite normal cover is diffeomorphic to. So starting point is this. Now, by the Kapovich-Wilkin, the fundamental group has a normal nilpotent subgroup boundary index. If I assume this is, I take a universal cover just modulo the nilpotent part, I get it's homeomorphic to new manifold. I already know. Then, right, the finite, if the sequence collapse to a point, the finite cover collapse to a point, then I perform iterated, successive blow up, right? Then I should get iterated bundle. But if I start with a nilpotent manifold, it's actually, I don't need to go finite cover. I just get iterated bundles. The semi means you have to go finite cover. Okay, this is starting point. This is starting point. Then the key proposition is the iterated bundle over toroid, this one, on the infinite manifold, nilpotent manifold, homeomorphic to nilpotent, is actually restriction of sequence subbundles with fiber like this and basically like this, and each one is a principal TK bundle. So we establish this. If you recall that, we already have a criteria saying once you have a sequence subbundle satisfy this condition, then the total space is nilpotent, diffeomorphic to nilpotent. So after the proposition, we know that a finite normal cover is nilpotent. All right, diffeomorphic. So what is a proof for to prove this, right? You just from one point blow up, you want to say the idea is show that the one point blow up actually every point blow up you see the same local structure. So roughly speaking, you want to say something like this. One point blow up actually everywhere blow up the local model is the same. Let me state this the following way. Here you have to use patching elementary TK structures in the work of Trigger Gormall on constructing F structures. You start with a first blow up, you get a bundle. The fiber, right? The fiber, they have to do several blow ups, you get the fattest, the last one, last fiber. So the last fiber, you rescale the diameter of the last fiber. So you rescale the fastest rate of a collapse. Now you blow this up at this, right, at this scale. So it's not collapsed. What you see is you have local uniform closeness. Let me state the property, right? For any Z on this one, you look this scale blow up at Z, its ball with this side, series quantity dependent dimension. It's close to a product space, a flat product space, torus time space, a ball. Epsilon, you can give an epsilon at large, it can be smaller than epsilon. Here the key is anything. Also, the Euclidean part is no different. The torus part, what about torus part? Different point, you may get different torus, but the torus has controlled the diameter uniform bounded by the constant. And injected radius has a lower bound. So they're not even the point can shift, right? The torus roughly only finite many if you get right? They all very close, right? Only bounded many. So that's what we call uniform closeness. And that is really the ingredient where you can apply so-called trigger formal the construction for abstractors. I guess I already at 10. So I just mentioned that how you get this, right? I said earlier, so our geometry is uniform Raffenberger, and any close, given any scale, it's close to uniform Raffenberger. So that guarantee that, right? You have this property. You have this property because if you apply the zoom-in map of technique of capote working with the background geometry like this, right? In their conclusion, they say only a point large measure where the short bases can be comparable, the length. But with respect to this regularity, actually every point is, in this case, is controlled. So once you have this uniform closeness, so locally you can, right, the fast rate you get no collapse, but you get a torus, right? Torus action, right? Local cover get torus action. Then the next question is, can you glue them to a pincer bundle, to a bundle? And the nilpotent fundamental rule is nilpotent guarantee is a pincer bundle. Yeah, they need some work, but I have no time to do that. Basically, you use you already 10 minutes. Yeah, okay. Yeah, yeah. Here you have to use. Yeah, well. Okay. Yeah, maybe I should say this, right? So first, using the uniformness, you can at this scale you can cover the manifold with a fixed eye, with open side. Right. The open side satisfy, right? Whenever the intersection not empty, its content unitable for something. And you can have uniformness, you can have diffeomorphic Gromov-Hotte approximation to the uniform model, which is a flat. Then with the pullback action on this, you get the local free action. Right? This actually Raffenberg method and trigger coding theory. Right? And then if a two is intersection not empty, you can consider a larger, right? Because this local model actually by the contradiction argument, the size of the ball can be arbitrarily large, fixed but arbitrarily large. So you can consider larger size of the ball, you get this. Then using the transaction, you get actually the flat metric. Flat metric, if they are C0 close, then they are C infinity close, right? So that's basically so the regularity to glue these free torus sections, no problem. Yeah. So that's you glue to get the principle. Once you glue get the principal bundle, right? Use nilpotent, you know the holonomy has to be trivial. So principal bundle. Use the principal bundle, then you go back to the original manifold. You rescale the second fastest rate. Then this fiber all collapse to a point. The limit space based on the uniform, right, closeness. They also, you have orbit space, but you don't have a metric on orbit space. But locally, you can have it's close to right the same picture. Then you run it again, right? You get the base space is a torus bundle, right? It's a principal torus bundle. Then the fiber, right, would be the base space torus inverse image. You get a fiber getting larger. Right? Then you do this inductionally, you get you get sequence of subbundles construction. All right, so let me just stop here. But yeah, I apologize. I ran over time. Thank you for your attention. All right, okay. Let me just, I promise another picture. It's interesting. I took on this. This is two very good friends. They are been friends for a long, long time. Misha Gromov, Jeff Chigger. Yeah. The two giants in Riemannian geometry. Okay, so let's stop here. Thank you very much.